All right, so if you were absent the day that we did 2.5, then this is for you. Or if you just wanted to review heating and cooling curves, then this is also for you. So at the beginning of class, we reviewed phase diagrams. So I'll just go over these couple slides. If you feel confident in these two slides, you can just skip ahead a little bit. So this first question is saying, at 20 degrees Celsius and 2 atmospheres, what state of matter is this substance in? And so remember, these heating and cooling curves, you can look at them. Solid is always on like the left side, liquid's always kind of in the middle, and gas is in the like bottom right region. And so it tells you if this substance will be either a solid, liquid, or gas at a specific temperature and pressure. So right here, we are at 20 degrees Celsius. This is kind of tough to estimate because the scale is very imprecise. But let's say maybe 20 is like about here, and we're also at 2 atmospheres. So that may be like right here. So if we find where these two things meet, whoops, not quite there. We're about right here. So we are in the gas phase. Anything in this like yellow region here would be gas. So that's how you use a phase diagram to figure out what state of matter something will be in. Oops. You might also get a question like this. What is the boiling point at 30 atmospheres? And so just to kind of like refresh your memory on this, in between a solid and liquid, this would represent, like if you went from the white region to the blue region, that would represent solid to liquid or melting. And if you went the other way, then that line would represent the freezing point. So down here between liquid and gas, this curve right there, that represents, if you're going from the blue to the yellow, that would be vaporization. And if you're going backwards from the yellow to the blue region, that would represent condensation. And then down here, just a reminder, solid to gas would be sublimation, and then gas to solid is deposition. So if we had 30 atmospheres, so I'm going to guess probably like right here, follow that over, and then drop it down. I'm thinking that our boiling point might be like high teens, low 20s degrees Celsius. So you should have had something in that range if you were reading this graph. All right, whoops. So now we're going to get into the actual 2.5 lesson. Gosh, I cannot write on this thing. We'll just do that. Okay. So we are talking about these things called heating and cooling curves. And so what this heating curve is, so that you're going to copy this down on your 2.5 paper if you didn't do that yet. This is just going to tell us the temperature. So like usually you'd have temperature on the y-axis, and on the x-axis you would have time. And so it shows you that as you increase the temperature over time, you go from solid, liquid to gas. So some things to note here. On the inclines, so from A to B, we have pure solid. As you can see, the temperature is going up, which means the kinetic energy is going up, because kinetic energy is just measured with temperature. This slope here from C to D, we are purely in the liquid phase. Temperature and kinetic energy are going up. And then from E to F, we are purely in the gas phase. So in between, in those plateau regions, notice that the temperature is not changing. So that means that the kinetic energy is also not changing. During phase changes, the temperature or the kinetic energy does not change. However, the potential energy does change. So here, because overall we're having like an increase in temperature, this is a heating curve, the potential energy is increasing. So from B to C, we've got solid and liquid existing together. This represents the melting point. And then from D to E, we've got liquid and gas existing together, and this represents the boiling point. So you saw this in your lab that you completed, what day is today? Tuesday. So you'll notice that when that solid ice started to melt, or when that liquid water started to freeze, you should have seen a plateau in your graph on the software, the Vernier software. And that's because the temperature wasn't changing, so the kinetic energy wasn't changing, but the potential energy was. So that means, this is a question that you would see on like a quiz. That means that the liquid phase first starts appearing here at B, and the gas phase first starts appearing here at D. So from B to C, just imagine like an ice cube melting. And from D to E, just imagine like water boiling. So from B to C, you can see the solid, you can see the liquid. And from D to E, you can see the liquid, and you can see the bubbles or the gas forming. All right, so next, this is a cooling curve. This is just the opposite, but basically the same stuff. Instead of the energy increasing because it's getting warmer, it is just decreasing now. And so we also have different names for our phase changes. So that, oops, I don't really mean to cross it out. So condensation would be here and freezing would be at this plateau. A little trick to help you remember, at the plateaus, so those like flat parts in the graph, the potential energy changes, but also the phase changes. And what I mean by that is like melting, freezing, boiling. So if you can remember, the three P's go together. Plateaus, where you have potential energy changing, and where you have the phase changing, then that can kind of help you keep this stuff straight. So then I had everybody answer these questions. So during which segments does the potential energy increase? Take a look at it. Potential energy starts with a P. And hopefully you said the plateaus. So these are the two spots where potential energy increases. So kinetic energy, remember kinetic energy is just measured with temperature. So the kinetic energy is changing at the inclines or at our slopes. So A to B, C to D, E to F. Which segments are there two phases of matter existing together? So that would be at our phase changes, because right here we've got solid and liquid because it's melting, and right here we've got liquid and gas because it's boiling. Temperature increase, obviously, is where you can see that it is moving up because temperature is measured on the y-axis here. And so if the slope, or if like the line is moving upward, then temperature is moving upward. At what point does the gas phase first appear? So I know that this is where it's purely gas. Like writing with a highlighter, so it might be kind of hard to see. But this part here, this is where the gas phase first appears. Because this is where you're first going to start see that liquid boiling. So like, when you have a pot of water on the stove and it first starts to boil, like you just see like little teeny tiny bubbles. That's when the gas phase is first starting to appear. So then the liquid phase would first start appearing right here. The substance would be boiling here. And then how many minutes does it take to completely vaporize a substance at its boiling point? So this is going to be something that you need to take from a graph on like your future quizzes and tests. So this is where it's boiling. So how many minutes does it take for it to fully boil while it's at its boiling point? And in this situation, it took from 80 minutes to 100 minutes. So grand total of 20 minutes. You can see down here that at the melting point, it only required 10 minutes. And that's just because it doesn't require as much energy usually to melt something as it does to boil it. So you just need to like apply that heat over a longer period of time. All right, the next thing. So heat of fusion, often given this symbol. Fusion is another word for melting. So I'm not talking like nuclear fusion here. This is just like something melting. And so this is like the change in H, or like the change in heat required to get something to melt. That's what this essentially means. A little bit more technical, it's the amount of energy, which we're going to measure in joules, required to melt 1 gram of a substance when it's at its melting point. And then the heat of vaporization, same thing, except instead of melting this time, we are just dealing with the boiling, but still the same type of term. Just this one is abbreviated vape and the other one is fuse. So you are going to get examples where you need to be able to calculate these things. So for this one, I always tell students the first thing you should do, underline the things that you're given in the problem. I'm not going to give you any irrelevant information. I'm just going to give you the info you need to know. So the heat of fusion of water is 333.55 joules per gram. How long would it take? That's what I need to calculate. So that's going to be time or minutes. To melt 3.5 grams, there's our mass, of ice when heat is added at a rate of 500 joules per minute. So starting with delta H. So whenever you have to calculate how long something takes, there's different ways to do this, but I'm just going to teach the same way every time, just to keep it consistent. Start with your delta H. So we have 333.55 joules, and I can write that as a fraction because it means that it takes 333.55 joules to melt 1 gram of ice. So we have, these are always going to be like 3-steppers. So if I'm trying to get to time, I'm trying to get to minutes, that means that I need to get joules and grams to cancel out by doing dimensional analysis, and I need to get minutes as my final unit. So minutes would need to be on one of the tops. So let's see. What's our first thing we could do to get joules and grams to cancel out? So we used this one already. Let's get grams to cancel out. So if I put 3.5 grams up here, I'll just put a 1 under there as a placeholder. It's not really necessary. Then my grams will cancel out. So if I stop here, my answer would be in joules. I don't want joules. I want minutes. So I need to find a way to get joules to cancel and get minutes on top. Use that. So this is the only thing that I've got left. Notice how this would be 500 joules per 1 minute, but you can flip that because those are equivalent ratios. So if we write it as 500 joules on the bottom per 1 minute on top, this gets my joules to cancel out. And then the only thing I'm left with is minutes, which is great because that's what I want. And so to calculate 333.55, multiply all the numbers on the top, divide all the numbers on the bottom. You're going to see a lot of ones here. Skip the ones, you don't need them. So for this one, if I round for sig figs, my answer is 2.3 minutes. And that's because these ones here are like infinitely significant. They're like given values. So my 3.5 is what's determining how many sig figs I can have in my answer. So yeah, this is just showing you how you can use dimensional analysis, and you can kind of like manipulate the information that you're given and get to the unit that you are looking for. So last example, and I will end this boring video. So for this one, I've already underlined my givens. I've highlighted my wanted. So when you need to calculate delta H, you're just working backwards. So notice how here we started with delta H to get to minutes. When you need to calculate delta H, start with minutes. So we're going to start with our 13.56 minutes. We'll do our 3 steps. And if I'm calculating delta H, the final unit I'm trying to get to is joules per gram. So I'm trying to get joules on top, grams on bottom. So I need to find a way to cancel out my minutes first. So let's go ahead and use, so we already used this. Now we want to cancel it. This one. This is the only other one that has minutes in it. So 500.0 joules per 1 minute. All right, so this gets my minutes canceled. Wahoo. Now I want to get my grams on the bottom. So now I'm going to do my 3.5 grams, throw a 1 on top as a placeholder. So I'll take my 13.56 times 500 divided by 3.5. And my answer with correct sig figs gets rounded to 1900 joules per gram. So yeah, that is how you do those calculations. I definitely recommend doing more practice on these. You've got some on the back of this 2.5. You can also do 2.6, and there's some stuff on 2.8 as well. So that's it. Let me know if you have any questions.